Hello everyone. In this talk, we propose a novel prompting technique called MathDivide, which basically improves upon the mathematical reasoning capability of large language models. So I'm Saksham, and this project was done by me along with my project partner Ashutosh. These are the contents of the talk. Moving on to the introduction. So in our project, we delve into the analytical and logical reasoning abilities of large language models, specifically through the lens of solving mathematical word problems. Previous research have shown that models performing in zero-shot and chain-of-thought contexts have seen notable enhancement in their mathematical reasoning capabilities. Also, deconstructing complex problems into simpler subproblems have significantly improved the problem-solving accuracy of large language models. So in our proposed prompting technique, we leverage the strength of both these approaches. And in this presentation, we'll be showcasing how our method stands up against the current leading technique called MathPrompter. So on the left, we can see the MathPrompter prompting technique, and on the right, we have the MathDivide, which is our proposed prompting technique. For MathPrompter, first, the problem is converted into a template where specific details are replaced with variables. Next, they create two types of prompts: an algebraic prompt to define a mathematical equation for solving the problem, and a Python prompt to code a function that calculates the answer. These are fed into the LLM, which generates both the equation and the Python function. They then perform a computational verification step to ensure that the algebraic solution and the Pythonic solution match. Finally, they repeat this process a designated number of times, say n, and the value that is most frequently identified as the solution throughout these iterations is then deemed as the final answer. Moving on to the MathDivide prompting technique, our approach begins by breaking down a complex mathematical problem, let's say m, into a series of smaller and more manageable subproblems, m1, m2, up to mk. We input the natural language problem into the LLM, which then identifies key components and their interrelations. We also give a tailored prompt P, and based on this prompt P, the LLM constructs an algebraic expression EI for each subproblem MI that basically embodies the essential mathematical operations needed to solve it. Once the expressions are established, the LLM generates Python code PIC for each subproblem, computing the numerical values of these expressions. And each variable in the expression is treated as a parameter in the Python code. The subproblems are then solved sequentially if they are interdependent, or independently if they are not. The overall solution S to the original problem is obtained by synthesizing the solutions from each subproblem Si. This solution is compared to the expected output Z. If S differs from Z, we introduce a refinement prompt, say PR, based on human feedback to pinpoint and correct the error, basically enabling in-context learning for the LLM. If S matches Z, no further refinement is required. Moving on to the demo. So this is a ChatGPT window. This is the prompt, and then this is the math word problem. So basically, based on the prompt, ChatGPT has splitted the problem into 3 subproblems, has formulated algebraic expression for each subproblem, and has generated a Python code for each of the subproblem. And then finally, all the Python codes are executed to arrive at the final answer. In this case, the final answer is correct, so we did not require a refinement loop. Or while if the final answer would not have been correct, then based on where the ChatGPT made a mistake, we feed a refinement loop to ChatGPT. Moving back to the slides. Now let's talk about the model and data set. So we choose 250 problems from the Grade School Math 8K dataset, and this is one of the sample from that dataset. On the left, we have the problem, and then on the right, we have the solution for that problem. Then let's talk about the LLM models which we use in our experiment. We use both open source and closed source models. The open source models are a Llama 2 7 billion parameter model and Llama 3 7 billion parameter model. And closed source models are GPT 3.5, Turbo, and GPT-4. Moving on to the experimental results. The experimental results clearly show that our prompting technique, MathDivide, demonstrated a better accuracy as compared to the MathPrompter prompting technique for all the 4 LLM models. So in conclusion, we can say that our proposed prompting technique, MathDivide, was able to beat the performance of MathPrompter. And thank you so much for listening.